In this video, we're going to discuss the common phase transitions between solids, liquids, and gases. If we were to take and either compress or cool a gas, we would take and reduce the average kinetic energy such that the gas molecules, when they collide, will potentially stick due to the intermolecular forces. And this would be the process of condensation. Whereas if we take the liquid and heat it up and reduce the pressure, we can then get the intermolecular forces to break and then go into the gas phase. This is sometimes referred to as vaporization. The process of cooling the liquid will reduce the amount of kinetic energy, and this then can result in freezing, where the molecules become locked into position and form the regular repeating pattern of the solid, whereas the adding of heat to the solid can then break some of these intermolecular forces to allow the molecules to slide past each other, and this is the melting process. The last of the phase transitions is when the solid goes directly to the gas phase under low pressure conditions, and this is referred to as sublimation. A very commonly cited example of sublimation is what happens when dry ice, solid carbon dioxide, is warmed and heat can be added so that the solid goes directly into the gas phase. And this is something that many of you have probably observed. It is possible then for the reverse process of sublimation to occur, where the gas molecules have some of their heat energy come out so that the solid forms directly from the gas, bypassing the liquid, and this is the so-called condensation or deposition process. This sometimes happens on a cold day when there's high humidity in the air, and you may get frost forming on the windshield of your car. Elemental iodine is an interesting material because it has intermolecular forces which are purely based on London dispersion forces, but the fact that the iodine is quite large and fairly easily polarizable, it turns out that at room temperature iodine is a solid. However, it has a significant vapor pressure. It actually goes into the gas phase quite readily, and so heat can actually cause the solid to sublime. And so shown here is a picture of a beaker that contains elemental iodine in the bottom of the beaker on the left there, and we have placed a bowl of ice in the top of the beaker, and slowly the iodine is going into the gas phase as you see the purple haze form inside of the beaker, and at some point then iodine crystals begin to form at the bottom of the bowl of ice. And so this is an example of the sublimation process and condensation process. So in this slide, we're going to discuss the relative energies of the various states of matter and the phase transitions that occur. So on the y-axis here, we have the energy of the system, and you can see that the total amount of energy for the gas phase is relatively high. If we then were to reduce the amount of heat, we could get condensation down to the liquid. So in this case, that process is going to have an enthalpy of less than 0, or essentially it's an exothermic process. The opposite process of vaporization of a liquid is endothermic, so heat has to be placed into the system to go and break some of the bonds. And so likewise, the process of going from liquid to the solid has to be an exothermic process, so the enthalpy is less than 0. The reverse, the melting process, or the so-called fusion, is a process that would be endothermic, so the enthalpy would be positive. And those two processes require either heat being removed or heat added in the same amount. It turns out then that the sublimation process, where the solid goes directly to the gas phase, is an endothermic process. Enthalpy is greater than zero, whereas the reverse, the deposition of the gas to the solid, is an exothermic process. Turns out that we can quantify the amount of heat necessary to melt or to have these various phase transitions, and so we could talk about the breaking of the lattice energy of the metallic solid and for the breaking of the molecular forces for a molecular solid. This is typically quantified as the so-called heat of fusion. This is the heat required to melt 1 mole of a pure substance. In this particular case, then, for water, if we were to melt 1 mole of water from going from the solid state to the liquid phase at 0 degrees Celsius, this would require 6.01 kilojoules per mole of water. On the other hand, we can also talk about the breaking of the intermolecular forces of the liquid to go to the gas phase, and this could be the breaking of the ionic bonds that might be present in a liquid ionic solid, or breaking of the intermolecular forces in a molecular liquid. And in this case, this is the so-called heat of vaporization. It's the amount of heat required to either evaporate or boil 1 mole of a substance. And for water, this is a much larger value per mole, and so the heat of vaporization of water is endothermic. It's positive 40.66 kilojoules per mole. So it takes more energy to break the intermolecular forces to go from the liquid to the gas phase than to melt the water. So it turns out that this information can be put into a graphical form by looking at the Eating curve for a substance, and so shown here is a plot of the time that is necessary to add heat on the x-axis and the temperature on the y-axis. And so it turns out that if we start at a temperature well below 0 degrees Celsius, we would have the solid form of water, which is ice. If we add heat over some period of time, the temperature will rise until it reaches 0 degrees Celsius, at which point the phase transition will start to occur, in which melting would be the process that is occurring. In this particular case, the temperature does not change, but the heat that is being added is going to break some of the intermolecular forces, and hence the average kinetic energy, or the temperature, is not changing. Once all of the ice has melted, then the temperature can begin to go up again. In this case, then we would have the liquid becoming warmer. At some point, we would reach 100 degrees Celsius, and the liquid water would no longer change temperature, and we would begin to have another phase transition. This would be the point at which boiling would begin, and this is when the liquid becomes the gas. As a result, then, the length of the horizontal line for this phase transition turns out to be quite a bit longer for a given amount of water as compared to the length of the line when the melting occurred. This is directly related to the heat of fusion versus the heat of vaporization. Once all of the water has gone into the gas phase, then the temperature can go up again, and we have steam, and this is then the final portion of our heating curve.